This lecture is about predicting with trees. Trees allow you to predict with functions that can capture nonlinearities much more easily than linear regression models can, but they take a little bit more thinking to learn about upfront. So the key ideas here is that we're going to have a bunch of different variables that we're going to be using to predict, and we're going to iteratively split those variables, use those variables to split the data into groups. The goal is to use the variables to split the data where it's maximally predictive. And the way that we're going to do that is by measuring homogeneity, how similar the objects that we're putting together in one group are. And what we would like to do is maximize the amount of homogeneity within each group. Often fitting multiple trees can work better in terms of getting higher prediction accuracy and maybe even some more stability, although it may be at the cost of a little bit of overfitting. We're not going to be talking about that in this lecture, but next week we'll be talking about fitting what's called random forests. The pros of this prediction approach is that it's easy to implement. You can interpret them very easily, and in fact, it's the sort of thing that you often think about when you think about predictions. We'll talk about that in a minute. It's better performance in nonlinear settings than things like linear regression or generalized linear models. But the cons are that without some sort of pruning or cross-validation, it's very prone to overfitting. It's hard to estimate uncertainty even under cross-validation, and the results can be very variable in the sense that if you leave out a few of the observations that you have, you might get a very different tree predicted at the outcome. So here's an example of the type of classification tree that we're going to be trying to build. In this particular case, the goal is to try to predict whether a county was going to vote for Barack Obama or Hillary Clinton in the 2008 primary. The way that was performed, the way that the prediction algorithm works, is it goes through and it looks at each variable and it calculates the optimal split along that variable, then looks within each subgroup and looks for an optimal split there. So the algorithm first identified that if a county was more than 20% black or African American, then the county was very likely to vote for Obama, and so that the prediction would be that Obama would win the county. And in fact, in a very large majority of the cases, that was true. Obama won those counties. If the county was less than 20% African American, you would follow the prediction algorithm down this path. The next question was whether the high school graduation rate was higher than 78% or not. So among those counties that were less than 20% African American, if there was a less than 78% high school graduation rate, it was very likely that Clinton was going to win those counties. And so the prediction algorithm said Hillary Clinton would win the county. If the high school graduation rate was greater than 70%, then you would continue to follow the prediction algorithm down farther and farther. In each case, you would put more and more constraints on whether the variable was on more and more variables. But at the end of the day, these leaves told you which predictions of which candidate were going to win the counties. So the goal of a classification tree is to do something like this. Build a classifier where you split variables one at a time, and you try to assign the prediction to be the most likely prediction at the end nodes of this tree, which are called leaves. So the basic algorithm is the follows. You start with all the variables in one group, then you find the first variable and split that best separates the outcomes. And when I talk about separating the outcomes, I will talk about in just another slide about a measure of homogeneity. Basically, you want each group to have a very homogeneous set of outcomes. Once you've divided the data into the two groups, into two leaves at a particular node, then you go within that particular group and you perform another split, trying to find the best variable or split within that separates the outcomes within the previous split. So what you're doing is you're recursively doing a set of nested splits where you start off with splitting the best variable. Then in group one of the data that you've left, once you've done that first split, you look and see if there's a split to be made within that group. Then you go and look at group two from the first split and see if there's a split to be made in that group. You continue until all of the groups are too small or sufficiently pure by your standards of purity or impurity. So here are some examples of measures of impurity. You don't have to be too intimidated by math. I'll try to explain in sort of intuitive terms what these mean. So what this p hat is, it's the fraction of the variables that you've assigned to group M that have outcome k. That's all that this equation means here. So it's the fraction of variables, or sorry, the fraction of observations that you've assigned to group M that have outcome K. So the misclassification error is just 1 minus that number. In other words, it's if you have a group where all of the observations have exactly one outcome, then the misclassification error in that group is equal to 0 because the fraction is equal to 1. All of the observations correspond to one particular uh, group. The Gini index is actually it's actually used very often in economics, and it's a measure of imbalance. And so what you can see here is it looks a little bit like, if you know something about the binomial distribution, it looks a little bit like a sum of the variances of the binomial of the estimated values from the binomial distribution. So this Gini index is actually maximized when you have exactly, say if you had two groups or two possible outcomes, this index would be maximized when each of the outcomes had exactly half of the observations within a group. Then there's the cross entropy or deviance. This is a slightly more complicated formula, but it also measures the homogeneity in a way that if all of the members of a group have the exact same outcome, the entropy will be very small. Whereas if all of the members of the group are sort of randomly coming from different outcomes, then the impurity will be very large. So the goal is to try to find splits that make the measures of impurity smaller than they were before. So we're going to talk about an example, and this is sort of a classic classification example. It's called the IRIS data. And so you can load that with data IRIS in R, and you can look and see that it gives you a few different variables, the sepal length and the petal length, as well as the width, and then a species classification. So these are the different species of iris that we're looking at in this data set, and so there's 50 of each. And for each one we have measurements of their properties. And so the goal is to try to classify these different observations into which species they are. So I can plot here the petal width versus the sepal width, and then I can label them with colors, the points with colors according to which species they belong to. And so you can see in this example there are three groups for corresponding to three species, and they seem to be pretty well separated by these two variables, so we'd like to be able to predict them on the basis of those variables. So what we can do is we can actually build a tree model using the tree function in R. So we load the tree library, and then we pass to tree a very similar formula that we would have passed to an LM or GLM object. On the left-hand side of the tilde is going to be the outcome variable, in this case species. On the right-hand side is going to be the variables we're using to predict, in this case sepal width and petal width. And then we have to tell tree which data set to draw those variables from. So in this case, we tell it to draw it from the IRIS data set. If we look at a summary of the resulting object, it tells you the number of terminal nodes, or the number of leaves that end up occurring in this classification tree. And then it tells you something about the residual mean deviance. So that was that measure of impurity that we had, the last measure of impurity that we talked about. And it also gives you a misclassification error rate, or how often out of these 150 samples within this particular training set you misclassify. So this is a very, very low misclassification error rate, but again, remember that that's a calculated error rate resubstitution, not performing cross-validation. So then you can plot the tree. So if you type plot tree, you'll just actually get the lines drawn here. You won't actually get the words. To get the words, you have to say text tree. So what this tells you is the first split happens on petal width. So if we're using those two variables, it says, okay, if the petal width is less than 0.8, we're going to classify you as setosa. And if you're greater than 0.8, you follow this path. Then again, we split on petal width. So that seems a little bit surprising, right? We split on the exact same variable we split on the first time, but now this variable is good at separating out Virginica from the other types of iris. And so then we can go over here and follow the tree down if petal width is less than 1.75. So again, remember this has already been greater than 0.8. So now it's between 0.8 and 1.75, and then it continues to split and so forth down the way. So another way that we can look at this, when we have just two continuous predictors in the models, we can actually plot what those splits look like in the two-dimensional space. And so what I've done here again is just plot the petal width versus the sepal width, And again, these are colored by the species that they belong to. And so then what you see here by using partition.tree with add equals true, it will just overlay these lines on top of the plot. And so we can actually see that if you're sort of in this box over here, we're going to classify you as Setosa. And if you're in this box over here to the right, we're going to class you as Virginica and so forth. And so what you can see here is actually the misclassifications. So for example, these two green spots are misclassified, as is this one red spot right here. And so when you have two continuous variables, you actually see this sort of nested set of boxes, which is what's happening with the classification tree. It's basically splitting you can imagine, so it splits one variable at a time. When it splits a variable, it just either draws a horizontal or a vertical line through this plot and says all the variables to one side or to the other get set to be one particular value. So this gives you an idea of what the classification looks like actually on the value of the observed data. This only works if you have one or two continuous variables. If you have more variables than that, you can't actually draw this diagram that shows where the cuts will be occurring. But you can imagine in bigger dimensional space, it's still just a sequence of boxes that you're drawing in that space if you want to think about it mathematically. So how do you predict new values with the functions? You can actually do that by, here I'm going to actually generate some new data. So here I'm generating new petal widths and new sepal widths, and I'm generating them from a uniform distribution. Here the uniform distribution to represent sort of the similar values that we observed in our real data. And so then what I do is I just apply the prediction function, or the predict function. Again, this is the exact same function I used with LM, but now I pass it, instead of the LM object, I pass it the tree1 object, and I pass it again a data frame with the new data in it. Again, the variable names in new data have to match exactly the variable names you use to build the tree model. If I look at the predictions, then I can look at, it reports the probabilities of being in each of the particular species given that data set. So for data point 1, it has probability 0.97 of being Virginica and 0.022174 for being versicolor and so forth. And so what you can do is then actually calculate a prediction value for each data point and plot them similarly to what we plotted before. So if I calculate these predictions and I say type equals class, so now what this is doing is instead of returning a probability, it actually returns only one value per data point. So what it does is it actually calculates the max probability in each row. So this is data point 1, the max probability is here. In row 2, the max probability is here. In row 3, the max probability is here, and so forth. And so now what I can do is I can plot the new data points that I've generated and color them by their predictive values, and then show you again the partitioning of this space according to what the prediction should do. And so in this case, you can see that all the colors within one box are all the same, and that's not surprising because this box always predicts any point that lands in this box always gets the same predictive value, and I'm coloring these points by their predictive values. So all this shows you is that within each different box, you get a specific prediction. So if your data point falls within a specific box, you get that color. So I'm going to show you an example of pruning. So the trees that I've built so far have been built to a specific stopping point, which is specified in advance in the tree function. But that stopping point isn't designed by cross-validation or any other steps, so it's not always clear that you won't get overfitting if you directly use the tree without doing any pruning. So to do this, I'm going to actually use an example that has a few more variables. So this is the CARS 93 dataset in the mass package. So if I look at this dataset, you can see it has the manufacturer, the model, the type, and then a bunch of other variables about specific types of cars. And so for this example, what I'm going to be trying to do is I'm going to try to predict the drivetrain, whether it's front-wheel drive, rear-wheel drive, or four-wheel drive, based on the other variables in the data set, in particular based on the miles per gallon in the city, the highway, the airbags, the engine size, width, length, weight, price, and so forth. So if I fit this tree model and I plot it, I actually see it's quite a dense model. There's quite a few different splits that happen in this model, and it's not surprising. We have a lot of variables to choose from. So by including more and more splits, we can get better and better measures of impurity. So what we can do then is we can actually cross-validate that model. We can use the function that comes with the tree package called cv.tree. And so there's two different ways that you can calculate the CV tree function. And it depends on what you tell it to do in terms of method. So if you set the method to be equal to misclass, it will tell you the number of misclassification errors. And if you tell it, if you don't give it the default is actually just the deviance. So this is the deviance impurity measure that was the last error measure we talked about. So what I can do now is I can apply cross-validation, and I can plot what happens for different sizes of the model. And so what I can see here is that as the model increases in size, I start off with having about 35 misclassifications, and then when I have a model of size 6 or bigger, between 6 and 9, I have much fewer misclassifications, and then I jump back up and have greater misclassifications again when my model becomes too complicated. So this is, remember, this is not resubstitution error rate. The resubstitution error rate will always get smaller as you include more and more splits. So if you just are trying to predict the training set, you can always do better by including more splits. But if you're doing cross-validation, you're trying to predict on a new data set, if the prediction doesn't generalize well, for example, if it's too complicated, it might not predict well on a new sample. Here we actually have the prediction errors that you get from on the deviance scale rather than on the misclassification scale. And so in this case, I've decided to use the deviance scale as the prediction model that I'm going to be using for further analysis. So what I can do is actually apply this prune tree function. And what I'm going to do is I'm going to say, give me the best tree that has exactly 4 terminal leaves or terminal nodes in the tree. And so I take the original tree that I fit that had a large number of splits in it. I tell it to give me the one that has the best 4 split tree. And so what I can see here is it just gives me a smaller subset of splits. In this case, it gives me these 3 splits on miles per gallon city, mile per gallon highway, and then on the width of the car to tell me whether I'm front or rear wheel drive. And I can see that this is the new tree that I could use for prediction that is actually going to have a smaller out of sample error rate than the tree that I would have created if I had just grown it without doing any pruning at all. Here I'm showing the resubstitution accuracy from the 2 different models. Here first is the prune tree. This is the tree that had fewer leaves, and so you can see that it actually has a few more mistakes that it makes than the model where it has the complete model with all of the leaves in it. But this is again the resubstitution error, and so even though it works a little bit less well on the observed data set that we have, the cross-validation results suggest that on a new data set, this would actually perform better than the prediction that we get from the full model that actually has fewer errors when you're doing resubstitution accuracy. So it's important to keep in mind that sometimes the simpler model that's less perfectly tuned to the data set that we have actually predicts a little bit better when you have a new data set. So some notes and further resources. First, I'd recommend both Hector Kurata Bravo and Cosmo Shalizi have very excellent notes on classification and regression trees. Hector also has some code that is useful for looking at how you do these sorts of predictions. The Elements of Statistical Learning book and Classification and Regression Trees books are both very, very good. Elements of Statistical Learning is free. And then we're going to be talking about random forest next week, but I thought I'd give you sort of a link to random forest so you can start taking a look if you want to start using it for your project or if you just are curious about how random forests work.